All right, guys, welcome back. Today we're going to talk about this idea of equilibrium. Equilibrium is going to tie into our understanding of forces, and we're going to be doing this right after we've learned about Newton's first law of inertia. So let's talk a little bit about forces and equilibrium. Oops. Wow, there we go. Okay. Things that are in balance with one another illustrate equilibrium. So, what you want to think when you hear the word equilibrium is balance. So, when forces are balanced, they are in equilibrium. Things in mechanical equilibrium are stable without changes of motion. The rocks are in mechanical equilibrium. An unbalanced external force would be needed to change their resting state. So, in other words, if I looked at picked one of these rocks here, it would have a certain weight pushing down on it. It would have a support force pushing up on it. And since that rock is not accelerating up and it's not accelerating down, it's just standing right in place, then it's just going to stay still. It's going to be at equilibrium. We don't know what these forces are, but we know that they must equal each other. There's a little tug of war going on, and right now those forces are balanced and that rock is not accelerating. Let's take a look at the next one. So what's a force? A force is needed to change an object's state of motion. So in order to cause something to move that's at rest or cause something to come to rest that is moving in a constant velocity, it needs a force. That's Newton's first law, which says that an object in motion will stay in motion and an object at rest will stay at rest unless there's an outside force that goes into changing the object's motion. So if you have a car driving along, if there was no friction between the car and the road, it would go, well, first it'd be really hard to start. But let's imagine that you're driving your car along and you hit a patch of ice and it's a super slick patch of ice. You're going to slide along at a constant velocity after you hit that piece of ice until some sort of outside force causes your car to come to a stop. That could be a tree, that could be an embankment, or maybe you get to a part of the road again that has some friction and your brakes will allow you to stop at that point. So things will stay in motion if they're at motion, or stay at rest when they're at rest, unless they're acted on by that outside force. All right. Scrolling is weird right now. I don't know why. Okay. Force. So let's talk about net force. Net force means the combination of all forces acting on an object is called net force. We add up all the forces on the object, that's a net force. A force in general is a push or pull. We talked about that in the last lecture. So when you push on something or you pull on it, you're exerting a force on it. A force of some kind is always required to change the state of motion of an object. The scientific unit of force is called a Newton, and it's abbreviated N. So when we're talking about net force, you can imagine this as a sort of tug of war here. You've got person A, person B, and between them, they've got a rope. And let's imagine that there's a little flag on the rope. As long as person A is pulling with the same force is person B. That flag is not going to move. This point on the rope is going to stay in equilibrium. It's going to be unmoved because the person here is pulling with the exact same amount as the person here on the right. Now, if person, give these A and B, if person A pulled harder than person B, now there's a net force in the direction of person A and the flag moves to the left. If person B comes back and tugs even harder, well, now it's going to go to the right. As soon as those forces become unbalanced, you get an acceleration in the direction of the stronger force. All right, let's look at the next slide. Here we have a little example. The net force depends on the magnitude and direction of the applied forces. So we have two key words there, magnitude and direction. Magnitude means how hard you push or pull. And direction, well, tells you the direction that you push or pull. So we have how hard you push or pull and the direction that you push or pull. So let's look at this little picture here. We have some sort of weight. We have one person pulling with 5 newtons and another person pulling with 10 newtons. These are pretty weak pulls. 5 newtons is about 1 pound of force and 10 newtons is about 2 pounds of force. But because they're both going in the same direction, it would be the same thing or equivalent to one person pulling with 15 newtons of force to the right. I want to point something out here. See how I drew this arrow longer? These arrows are called vectors, and they indicate the magnitude and direction of the force. So this longer vector indicates that it's a stronger force than either of these. In fact, we should be able to, if I drew this properly, take the length of this 5 Newton vector, add it to the length of this 10 Newton vector right here, and when I add those two together, get this 15 Newton vector. So 5 to the right plus 10 to the right equals 15 to the right. Let's look at our next example here. We already showed this one, 5 to the right plus 10 to the right equals 15 to the right. Now we have a situation where you have people pulling in opposite directions, forces in opposite directions. But the magnitudes are not the same. We have a 10 Newton pull to the right and a 5 Newton pull to the left. I bet you guys can figure this out. So our resultant force is going to be a 5 Newton pull to the right. Notice I drew this like a short arrow to match the length of this arrow right here, because that's the same length. They're both 5 newtons, just this one's to the left and this one's to the right. This should make sense. If you have your 10 newtons pulling to the right, you have a strong person on this side and a weak person on the left, then it's going to get pulled to the right. But it's not going to get the full force because this person on the left is doing something. So we just add up their forces and we end up with 5 to the right. Right, here's our final little square on the grid. Now we do have balanced forces. We do have that equilibrium state where the force on the right is balanced with the force on the left. So if this was at rest and we pulled at this amount, guess what? It's still going to stay at rest. We're going to have 0 newtons acting on this because they're going to cancel each other out. So equilibrium, the forces are balanced. The forces to the left equal the forces to the right when we have an equilibrium scenario. So this third scenario here, this is equilibrium. These first two are not in equilibrium because the net force is not 0. It is 15 in this one, and it is 5 in this one. All right, let's do another little example here with net force. When the girl holds the rock, sorry about that, with as much gravity upwards, or with as much force upwards as gravity pulls downward, the net force on the rock is 0. All right, let's talk about that a little bit. Earth's pull on the rock, how much the rock pulls down or is pulled down by the earth, is called the weight of the rock. So we have the weight of the rock pulling it down, and we have the little girl hand pushing it upward. Her hand's providing a support force. Okay. Right now, when they're in equilibrium, that rock is going to be unchanged. Just like if I have my cup of coffee right here, which you should be able to see on the screen. When I hold it like this, my hand is pushing upward on the bottom of the coffee, and I can feel the weight of the coffee cup pushing down. Now, if I push upward with greater force than the weight of the coffee cup, it moves up. If I relax my muscles and stop providing that support force, then the coffee cup pushes down and moves down. So here we have a balanced scenario. I'm pushing up with the exact same force that the cup is pushing down, with, which is its weight. If I exert greater force, the cup gets lifted. If I exert less force, the weight of the cup pushes it down. We can talk about this in terms of tension too. Tension is force along a rope, a chain, or a spring. Usually you think of something hanging like this. So if I look at my cell phone here, hanging from its charger, there is a tension force in this rope that is holding the cell phone up, and the weight of the cell phone is pulling it down, right? So we have the weight acting down, and we have the tension in the rope acting up, which allows the cell phone to be at equilibrium. And I could sketch that out like so. We have the weight of the cell phone acting down, and we have the tension acting up through the cord, the charging cable there on the cell phone. And as long as the cell phone is not moving up or moving down, we can say that this is at equilibrium, and that the forces up have to equal the forces down. And furthermore, we know that the forces down are equal to the weight of the phone. So the tension, which is the upward force, has to equal the weight of the phone. So however much my phone weighs, that's equal to the tension in the charging cable there that was holding it up. If we look at this little example they have here, where we have a spring scale, which means that there's a little spring in here, and it's connected to this hook. And when you pull down on the hook, it stretches the spring, and then that will change the reading on the scale. You might have one of these at your grocery store if you're weighing bananas or something like that. The tension in the string has the same magnitude as the weight of the bag, so the net force on the bag is 0. The bag of sugar is attracted to the earth with a gravitational force of 2 pounds or 9 newtons. So if we put a bag of sugar on here, now we have the weight of the sugar being pulled down, and we have the tension, or the weight of the sugar acting down, and we have the tension acting up. And again, we know that the sum of the forces, I'm going to use some new notation here because I will use this periodically. There's a whole bunch of different ways to say net force. We can say net force and write it out like that. Sometimes we'll write the F with the little subscript of net. And sometimes we'll use the Greek symbol sigma. This is the mathier way to do it. Sigma F, which means sum of forces. As in, we add up all the forces. So net force, F net, sigma F, sum of forces, all mean the same thing. And when they're in equilibrium, they all equal 0. So here, if we say the sum of the forces equals 0, and when I sum the forces, I take the forces up minus the forces down. I end up with the forces up equaling the forces down when I subtract that over. Give myself a little room to work. The force down is the weight. And the force up is the tension. So again, we have the tension up equaling the weight acting down. And as that weight goes down, you'll have the reading on the spring scale go down, or we'll have this little lever go down as well. So if we put a heavier bag of sugar on there, then this would go down even further and give us a higher reading to indicate more weight. I think I already said this. There's 2 forces acting on the bag of sugar. The tension force is acting upward. The weight is acting downward. The 2 forces on the bag are equal and opposite, and the net force on the bag is 0, so it remains at rest. We can say that force is a vector quantity, and a vector is an arrow that represents magnitude and direction. I talked about that on an earlier slide. A vector quantity needs both those, magnitude and direction. And a scalar quantity is magnitude only. So if we think about things that are vectors and things that are scalar, so things that have a direction are going to be vectors. So if I say I drove 20 miles an hour east, that's what we call velocity, and it tells you how fast you drove and the direction. And if I just say I drove 20 miles an hour, but I don't give you a direction, then we call that speed. So notice that the speed doesn't include direction, but velocity would. When we talk about force, I say I pulled with 300 newtons of force to the right. Now it has magnitude and direction. If I say it's 95 degrees outside, there's no direction in temperature, so temperature would be in the scalar. If I said I am, 6 feet tall, my height would be a scalar quantity. Time is a scalar quantity. So it needs to have both magnitude and direction. To be a vector. I'm going to skip some slides here. I think we talked about the length of the vectors. This vector represents a force of 60 newtons to the right. For some reason, they put kilometers per hour. So it should say 1 centimeter equals 20 newtons. So we have 20 newtons plus 20 newtons plus 20 newtons, because that's 3 centimeters long, which gives us a total of 60 newtons. Let's look at this, these little painter problems here. These come up in some of our homework. This is the sum of the forces upward equals the sum of the downward vectors in order to be at mechanical equilibrium. So let's ponder this for a little bit. Let's say that we have a painter here, and that this painter has a weight of 500 newtons. That means that it is acting downward. His weight is acting towards the center of the earth because gravity, 500 newtons. This guy looks a little bigger, maybe twice as big, so we'll call him 1,000 newtons of weight. We're going to see if we can figure out the tension in these two cables. Well, let's say that the tension here, which I will call T1 for tension in cable 1, is equal to 1,200 newtons. How would we figure out the tension in cable 2? Well, you might want to pause this here and see if you can figure it out on your own. The way that we're going to solve it is we're going to say the sum of the forces is equal to 0. So when I sum the forces, and really we could get extra precise and say the sum of the forces in the y direction, which means up and down, are equal to 0. That will be balanced in the y direction. Or we could just write it as the forces up have to equal the forces down. Well, what forces do we have up? We have tension 1, which is 1,200 newtons, plus tension 2, which is unknown. The forces down are 1,000 newtons, plus 500 newtons. So now I have 1,200 newtons plus T2 equals 1,000 newtons plus 500 newtons, which is 1,500 newtons. Subtract 1,200 from both sides. And I get T2 is equal to 300 newtons. So the tension in cable 2 is equal to 300 newtons. If I add this up, 1,200 plus 300, that's 1,500 up, and 1,000 plus 500 is 1,500 down. So that checks out. I have 1,500 newtons acting up, 1,500 newtons acting down. So we have an equilibrium condition here. Oh no, what did we forget in our analysis? We got the weight of the board. Let's redo this. Let's see what we can figure out. Let's again I'm going to have you guys do this on your own. Make this painter 500 newtons. Make this painter 1,000 newtons. And let's say that the weight of this board is 300 newtons. And now I'm going to give you T2 and say that it is 450 newtons. and ask you to find T1. So see what you can do with that and be ready to talk about it in class when we see each other. Have a good one, guys.